The final data structure in this course I'm going to cover, and quite briefly, is a graph. As you'll see, these, like working with trees and heaps, are often used indirectly to implement a more specific idea. Let me explain. Now first, to be clear, when we're talking graphs as a data structure, this is a totally separate idea from a graph as some kind of visual chart or diagram. Now we've seen linked lists, a collection of nodes with a specific sequence from one node to the next. We've seen trees, a hierarchy of nodes, multiple levels of parent and child nodes. But these have constraints. In a tree, each child only has one specific parent. Each parent has specific child nodes. A child does not have multiple parents. There's no direct link between sibling nodes, and certainly no links between different branches of the tree. But with the idea of a graph data structure, those limitations are off the table. A graph is a collection of nodes where any node can link to any other node, and a node can link to multiple other nodes, whatever is useful, whatever is meaningful. We could use a graph to model a social network with each node a person. People link to a couple of people who link to multiple other people who link to others who may very well cycle back to the first person. Now notice with this kind of structure, you don't have to have the idea of only one fixed starting node or one fixed root node. It makes sense that you could begin at any node to find and follow all the connections. Other examples might be for transportation, modeling the distances between cities, or for flight routing. We go from SBA to LAX or PHX. We can then go from any of those points to multiple other locations. We could model an Ethernet network in an office or in an entire building or a city. So graphs are great for anywhere where you need to describe a complex system of interconnected points. Okay, some terminology here. Because graphs in computer science are so closely linked to graph theory in mathematics, it is common to hear mathematical terms used. With linked lists and trees, we talked generically about collections of nodes. Well, in graph theory, we call these nodes vertices, and the connections or the links between them are referred to as edges. So a graph can be described as a set of vertices and a set of edges. We can also say whether those edges should have a direction to them. In some situations, it makes sense that any edge, any connection between two vertices is only one way. In other situations, you might want to be able to follow that edge, that link, in either direction. If the edges only go one way, it's called a directed graph, but if you can follow any edge in either direction, it's an undirected graph. Now, furthermore, if it's useful, you can also give every edge a weight. This is a way of associating a number, usually just an integer, with the connection between the two vertices, with each of the edges. Now, you could do this to represent, say, the distances between cities if you were trying to calculate the shortest route between multiple locations. Or you could use a simpler weight to indicate which edges take priority over other edges and which edges should be deprioritized in any logic you have, and this would be referred to as a weighted graph. All right, that's some basic terminology, but here's the thing. The focus of this course has been on practical and pragmatic data structures, things we can understand and then go ahead and create using the built-in libraries or frameworks of the common general-purpose languages. But there is no generic graph data structure in Ruby or Python or Java or C# or C++, because the implementation of any graph is always going to be more specific than that. And we already have used graphs in this course. A linked list is a kind of graph. A tree is a kind of graph. A heap is a kind of graph. They are all graphs with intentional constraints. A single linked list would be considered a directed graph. We can only go one way between nodes. There's a specific direction. Whereas a doubly linked list is a kind of undirected graph. We can follow the connection between nodes in either direction. And this is what I mean by this data structure is used to implement more specific pieces. Sure, you can create your own graphs. You can go to town with this idea. But at this point, folks, I'm going to intentionally draw the line. Graphs are an immensely interesting area, but they are situation specific, and further discussion of graphs would be a course by itself, and it probably wouldn't be a short course with the words foundations of anything in the title. So next, we're going to finish up this course with a bit of a recap and some suggestions for how to approach choosing the right data structures.